Understanding what makes up Earth's atmosphere and the factors that keep it steady is crucial for comprehending weather patterns. Let's take a dive into the basics that govern the layers above us. The Earth's atmosphere is composed of various gases, the primary gases being nitrogen, oxygen, argon, and carbon dioxide. The proportions of these gases, as represented in the table, provide insights into their respective volume percentages in the atmosphere. Nitrogen, 78%, oxygen, 21%, argon, 0.9%, and carbon dioxide, 0.03%. Structure of the atmosphere, troposphere. The troposphere, the layer closest to the Earth's surface, stretches from the ground up about 8,000 to 15,000 meters, or 26,000 to 49,000 feet. This is where weather events like clouds, rain, and storms take place. As you climb higher, the temperature usually goes down. Stratosphere. Above the troposphere is the stratosphere, reaching around 15,000 to 50,000 meters, or 49,000 to 164,000 feet above the Earth. The stratosphere is where you find the ozone layer, which absorbs and shields us from the sun's harmful ultraviolet radiation. Here, the temperature generally goes up as you go higher, thanks to the presence of the ozone layer. Mesosphere. The mesosphere extends from approximately 50,000 to 85,000 meters, or 164,000 to 280,000 feet above Earth. Temperatures in this layer decrease as you climb. The mesosphere is where most meteorites burn up upon entering the Earth's atmosphere. Thermosphere. Sitting above the mesosphere, the thermosphere spans from approximately 85,000 meters, or 280,000 feet, to the outer edges of Earth's atmosphere. In this layer, temperatures rise significantly as you go higher. The thermosphere is where the Earth's atmosphere meets the solar wind, which consists of charged particles from the sun. Exosphere. The outermost layer, the exosphere, extends beyond the thermosphere and lacks a clear boundary. It gradually transitions into outer space. This layer has very few particles, and the rare gas molecules present can escape into space. Satellites and other objects in low orbit are situated in the exosphere. Now let's turn our attention to the subject of atmospheric stability. By examining atmospheric stability, we can gain valuable insights into the behavior of the atmosphere and its impact on flight conditions. Using a parcel to assess atmospheric stability. In meteorology and aviation, an air parcel serves as a valuable tool for evaluating atmospheric stability within a specific vertical column of air. The process involves selecting an air parcel from a designated altitude, typically the surface, and virtually lifting it to a predetermined test altitude. As this parcel ascends, its temperature undergoes changes due to expansion and latent heat effects, as discussed in Chapter 12 of the Aviation Weather Handbook on vertical motion and clouds. The standard temperature lapse rate refers to the rate at which air temperature decreases with increasing altitude in a standard atmosphere. On average, the standard temperature lapse rate cools 2 degrees Celsius per 1,000 feet of altitude gained. In contrast, the standard pressure lapse rate relates to the decrease in atmospheric pressure with increasing altitude. In a standard atmosphere, the pressure decreases exponentially as you climb higher. The standard pressure lapse rate typically amounts to a pressure drop of about 1 inch of mercury for every 1,000 feet of altitude gain. Both lapse rates play a pivotal role in aviation as they impact aircraft performance, altitude calculations, and weather forecasting. The critical step is to compare the temperature of the lifted parcel with the ambient air temperatures. 3 possible scenarios emerge from this comparison. If the lifted parcel is cooler than the surrounding air, it becomes denser and returns to its original level. This situation indicates stability as the parcel resists upward displacement. When the lifted parcel matches the surrounding air temperature, it remains at the same level. In this case, the parcel is deemed neutrally stable. If the lifted parcel is warmer and therefore less dense than the surrounding air, it continues to rise independently until it reaches the same temperature as its environment. This signifies an unstable parcel. Greater temperature differences result in higher rates of vertical motion. Now that we've explored the concept of using air parcels to assess stability, let's dive into the various types of atmospheric stability which play a crucial role in aviation and meteorology. Stability types. The stability of an atmospheric column is categorized based on the distribution of parcel stabilities within that column, with the Earth's surface at the starting point and the column's top defining its depth. 4 distinct types of atmospheric stability exist. Absolute stability. In this state, the lapse rate of temperature in the atmospheric column is lower than the moist adiabatic lapse rate. This includes both isothermal and inversion temperature profiles, and an upward lifted air parcel would be colder than the surrounding environmental air, tending to sink back to its initial level. Neutral stability. Neutral stability characterizes an atmospheric column where an ascending or descending air parcel maintains the same temperature as the surrounding air. For unsaturated columns, it occurs when the lapse rate of temperature equals the dry adiabatic lapse rate, while for saturated columns it corresponds to the moist adiabatic lapse rate. Absolute instability. In an absolute unstable atmosphere, the column exhibits a super adiabatic lapse rate of temperature exceeding the dry adiabatic lapse rate. In this case, a vertically displaced air parcel accelerates in the direction of displacement with increasing kinetic energy as it moves away from its initial level. Conditional instability. Conditional instability pertains to a column of unsaturated air in the atmosphere. Here, the lapse rate of temperature is lower than the dry adiabatic lapse rate, but higher than the moist adiabatic lapse rate. An air parcel initially remains stable, but becomes unstable after ascending to a specific altitude above its lifted condensation level. This point, known as the level of free convection, defines conditional instability, where a parcel becomes warmer than the surrounding air and thus rises due to its buoyancy. These stability types provide valuable insights into atmospheric behavior, aiding meteorologists and aviators in understanding and navigating through various weather conditions.